the simple rule that limits all technology. Every invention feels like progress. Every breakthrough promises fewer limits. But technology has a ceiling, and it is written into physics itself. To understand what limits all technology, we must step back from machines. Power is not about intelligence. Speed is not about ambition. Every device obeys the same invisible boundaries, rules no engineer can negotiate. Early inventors believed limits were temporary. Better materials would fix them. Smarter designs would overcome them. More energy would push them aside. But physics quietly disagreed. At the heart of every machine is energy transfer. Energy must move from one form to another. Work must be extracted. Waste must be released. No process escapes this structure, and structure creates limits. The first warning came from heat engines. Steam machines could never reach perfect efficiency. No matter how refined a design, some energy always escaped as heat. Loss was unavoidable. This puzzled engineers for decades. They assumed flaws caused inefficiency. Better parts would solve it, but experiments showed otherwise. Even ideal machines failed to reach perfection. The problem was not design. It was reality. This led to a deeper realization. Energy has direction. It prefers to spread. Machines fight that preference. And physics charges a price. This price applies everywhere. Computers generate heat. Motors waste energy. Batteries leak power. Even information processing creates entropy. Technology cannot escape thermodynamics. This reframes innovation. Progress is not breaking limits. It is approaching them asymptotically, getting closer without ever touching. Physics sets the ceiling. Engineering climbs toward it slowly. Once this is understood, a deeper question emerges. If every technology is limited, what happens when we reach the ceiling? What does progress mean when improvement slows? And which limit matters most? Those answers reveal the quiet rule behind every machine. That rule is the second law of thermodynamics. It does not ban machines. It limits them. Every technological process creates entropy. Every calculation, every transmission, every movement of charge. The more work a machine performs, the more disorder produces elsewhere. At first, this seems manageable. Better cooling, smaller components, more efficient pathways. Technology hides entropy behind design, but it cannot eliminate it. It can only move it. This becomes obvious in computing. Each logical operation requires energy. Each erased bit produces heat. As systems shrink, heat density rises. Efficiency improves, but entropy accumulates faster. This is why supercomputers demand massive cooling. Why data centers consume enormous power. Why speed increases come with thermal walls. Information is physical. Processing it carries unavoidable cost. The same applies to energy generation. Power plants convert heat to work, but waste heat always remains. No engine can use all available energy. Some must be discarded to function at all. This limit is not technological. It is fundamental. Even a perfect engine obeys it. Even an ideal computer heats its surroundings. Nature demands payment in disorder. At first, this feels restrictive, but it explains patterns. Why efficiency gains slow over time. Why breakthroughs become incremental. Why scaling eventually hits resistance. Technology advances by fighting entropy locally, but the universe collects globally. Progress borrows against disorder, and the bill grows with complexity. This reveals why limits appear everywhere at once. In speed, in size, in density, in power. They are not separate problems. They share a common cause. Understanding this prepares us for the central conflict. If entropy limits all technology, can intelligence ever escape it? Can clever design outweigh probability? Or is there a final boundary no civilization can cross? That question defines the future of progress itself. This is where the tension becomes existential, because entropy does not scale kindly. As systems grow more advanced, costs grow faster. Early tools wasted little energy. They were simple. Modern machines are intricate. They concentrate power, speed, and information. And concentration accelerates entropy production. Complexity sharpens the limit. This creates diminishing returns. Each gain in performance requires disproportionate effort. More cooling, more materials, more energy. Progress slows, not because ideas run out, but because physics pushes back harder. This is visible everywhere. Clock speeds plateau. Battery improvements crawl. Miniaturization hits thermal walls. The universe allows improvement, but demands increasing payment. Even hypothetical technologies face this wall. Perfect recycling fails. Lossless computation collapses under noise. Infinite efficiency violates probability. Every workaround relocates entropy, never removes it. This places intelligence itself under constraint. Smarter systems manage entropy better. They delay loss. They optimize pathways. But delay is not escape. Entropy always waits. Civilizations face the same law. Growth concentrates energy and information. That concentration heats environments, strains resources, accelerates disorder elsewhere. Expansion carries a hidden countdown. This reframes the future. Progress is not infinite acceleration. It is careful balance. Pushing too hard shortens longevity. Efficiency becomes survival strategy. The second law does not kill innovation. It defines its shape. Success belongs to systems that respect limits early, that trade speed for stability, that optimize lifespan over peak output. Understanding this changes ambition. The goal is not to overpower physics. It is to cooperate with it, to design within limits, not against them. And that leads to the final realization. Technology is not capped by imagination. It is capped by entropy. And any civilization that forgets this will learn it the hard way. The climax of this story is sobering. The limit was never technical. It was physical. Entropy does not oppose invention. It taxes it. Every breakthrough must pay. Every system must shed waste. Progress is rented, not owned. This explains why no technology feels final, why upgrades never end, why perfection remains unreachable. Physics enforces diminishing returns relentlessly. The ceiling is asymptotic. This does not make innovation pointless. It gives it direction. The smartest technologies are not the fastest. They are the most balanced. They maximize usefulness per unit of entropy. They stretch time, not power. Civilizations that survive long-term will not be the most aggressive. They will be the most efficient, the most patient, the most respectful of limits. Entropy rewards restraint. This principle applies personally. Burning faster shortens lifespan. Pacing preserves structure. Balance extends opportunity. Physics echoes in life. The universe does not promise unlimited growth. It offers a narrow path. Those who understand the limits early can walk it longer. Those who ignore them burn out quickly. Technology is not about conquering nature. It is about aligning with it, working with entropy, not against it. That alignment defines sustainable progress. The simple rule limiting all technology is not a barrier. It is a guide, a reminder that power must be handled gently, because the universe always keeps the final account. Sometimes the smallest shift in perspective becomes the beginning of a new future.